All right, here we go. Our second pre-recorded lecture of the semester, and hopefully the only other one we got to do, but we'll see. Kind of got bamboozled by Ames School District, unfortunately. But here we are, and as you can see, I'm trying a new setup for this video because a lot of what we're going to do today is pretty visual, and normally, of course, I would just do some Beamer slides, but I got to draw some pictures today. So I'm trying this setup out. We'll see. It's a good excuse to use this iPad and Apple Pencil that I inherited. And haven't actually used for anything yet. So we're giving it a spin today. We'll see how it goes. I'm already fucking with the screen here, and I'm already cursing within a minute here. This video has been demonetized immediately. Anyway, all right. Plot for today. So, last time we established the Cauchy-Goursat theorem, and today we'll see, well, okay, how do you actually use it? And then that'll lead us into establishing a fundamental theorem for calculus for complex variables. So, cool. All right, things to be thinking about outside of class. Our second quiz will be taking place on Thursday next week. The review has been posted. After today, you can theoretically do every problem, but there's one of them that's going to be made way easier from something we're going to demonstrate on Tuesday. I'll let you figure out which one that is. Okay. All right, well, let's get going then. And, oh, hey, look at that. Ooh, wow, it's the future. Amazing. Okay, so what does the Cauchy-Goursat theorem tell us? It tells us that... Oh, I got it on the wrong thing here. All right, yay, all right. All right, Cauchy-Goursat says that integrals here... oh boy, yeah, look at this wonderful handwriting. Integrals are always equal to 0 here. Integrals of this form when things are particularly nice, where C is a simple closed curve. Oh my god, it's awful handwriting. It was working way better. Oh, let me see what I can do here for you. All right, do I got a tip sharpness? Oh my god. Let's do brush pen, maybe that looks better. Okay, and I played around with it a little bit. I thought this would work, but apparently it's not. Oh my god, look at the word simple there. Let me fix that. Okay, all right. Yeah, that's a little bit better, I think. Okay. And F is analytic on C and inside C. Okay. So this right here is, of course, the Cauchy-Goursat theorem, and it is quite useful, right? Because first of all, note, this tells us that basically every function that we care about, right, the analytic ones, their integrals are just super easy. Like literally, if you want to integrate on a simple closed curve and you have an analytic function, it's 0, period, done, move on. Right, so this immediately tells us that there are a whole bunch of functions where I literally have to do 0 work to integrate them. I don't need to figure out any derivatives or any of that stuff. I literally just go, boom, it's 0, I'm done with my life. Quite powerful, right? And as we noted, analytic functions, for the most part, are the ones that we like using, right? Polynomials, exponentials, sines and cosines. There are some functions that do fail analyticity. So for example, log is almost analytic everywhere, but it has a problem with the negative numbers, right? Because again, log is got argument built into its definition, and argument kind of goes a little haywire at the negative real numbers. Right, but for the most part, everything we're going to encounter is nice and analytic everywhere, and so integrals are just easy peasy. Right, so again, as we established for some quick examples, right, if you wanted to integrate, so for example, cosine, this is always equal to 0 no matter what. Pick any curve you can think of in the plane, it will integrate out to 0. And as we saw on a homework problem, so for example, z squared plus whatever the polynomial was, right, if you actually compute this thing by hand, right, by breaking this into its real and imaginary parts and parameterizing whatever the curve was, right, it sprawled out horribly, and you had a bunch of, like, sine cubed and cosine to the fourth power flying around, right, it quickly just turns into a huge mess, and those integrals are very difficult and greasy to work with. Greasy. Well, I say greasy, but it did. Beautiful. All right. However, while this is all well and good, the Cauchy-Grassat theorem requires a couple of things. First of all, analyticity, which, like we said, most of the functions we're going to run to are. But there are some pretty easy integrals to set up and then ask, well, what would these equal? So, for example, and this is going to be the one we're going to attack. All right, so, okay, this function right here is analytic everywhere except at a very specific point. Z equals I. Right, because it's just not defined at I. However, it's 1 over z minus I, and as we noted, all of the usual calculus facts about derivatives hold true. This thing's derivative does exist, and it exists everywhere it is defined, so this thing is nice and analytic. Everywhere except a certain point I. So C here, if C does not enclose the point I, then this is 0. By Cauchy-Grassat, right? Because you have a nice analytic function. The function is then defined and analytic on the curve and everywhere inside the curve. So if the curve C does not enclose I, then we are nice and happy and the integral is easily computed. It is equal simply to 0. Okay. So what if it does? Is there anything we can do? Right, and you may recognize from your homework, we computed a similar integral. I think it was just 1 over z minus 1, but it applies. So it was 1 over z minus a number, and the curve was enclosing that point, so you had to be, right, we couldn't just immediately go, oh, Cauchy-Grassat, we're done. Right, but we did note that you actually got a pretty nice value with that when you got 2 pi I, which is pretty neat. Okay. So, what we want to address now is, what if we have a function that is essentially analytic, but the curve's enclosing the exact spot where it's not going to be analytic? What can be done? Okay. So, here turns out to be the bit of the trick. So, let's say you've got a wonderful curve C. Look at that beautiful curve. And let's say that your curve C, inside of it, we've got another one, K. Look at that, excellent. Oh my god, it's awful. Get out of here. Oh my god. This is going swimmingly. Okay, and inside C, you've got K. Okay. Right, and now let's say we have a function f that is analytic on C, inside C, but not inside K. So basically it's analytic on the curve C, it's analytic everywhere inside, but anywhere inside K it's not. Okay, so what can we do? Right. Well, right, so if I tried to compute the integral of f on C right now, I can't use Cauchy-Grassat because I have no guarantee of the analyticity inside, so what do I do? Well, it turns out you could pull a bit of a sneaky, because let us connect these two, and here's where I needed to do some sort of drawing, so this is why we're doing this today. Let's say we connected the two now using some line segments, and we'll call this one up here L1, and we'll call this one L2. L2. Okay. So note, if I do this, I am going to create now two closed curves where f is analytic on the curve and inside the curve. So note this splits into two pieces now. So specifically, I'll have L1 L2, and then now here So I'll delineate them, L1, L2. And then here I'll have a piece of K, and we'll call that K1. And over here I'll have a piece of C, and let's call that C1. Right. And I'll pick up another piece, so note that's this component over there, and it will also break it into L1 like this, zip, 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 L2, and then I'll have a piece of K. Let's go, oh god, why did it switch to erasing? I did not ask you to do that. K2, and then a piece of C, C2, like that. Okay. So we can take our original closed curve C and our closed curve K like that, and if we attach them with two line segments, we can split them into two separate pieces. And then now we know that on these two separate pieces here, the integrals are going to equal 0. Because f is analytic on C and inside C, but not inside K. So in each one of these pieces, f is analytic on the curve and inside of them. So we'll call this piece T1 and we'll call this piece T2. Right. So by Cauchy-Grassot, we know that the integral on the left-hand side needs to equal 0, and the integral on the right-hand side needs to equal 0. All right, let's actually compute those out. So note that we know that the integral on T1 of f of z is equal to 0. Right, but how was that formed? Well, that was formed by integrating and combining up 4 separate pieces. So this would be the integral of C1 plus the integral of L1 plus the integral of L2, and then plus the integral of K1. Right. Okay, right, so if we just go back to our picture, all I'm doing is I'm integrating on T1, and I know that has to equal 0 by Cauchy-Grassot, and I'm just pointing out, well, it's 4 things glued together. Okay. Okay. Likewise, the same is true for T2. But here we want to point something out. So far with all of these pictures here, I have not indicated a direction. So let me get a different color now for this. Right, so remember, direction matters, especially if you reverse it. So the curve C, and again, we almost always orient things positively, is going like that. So we're going around the curve like that. And same thing for K. We're going to go around K in the same direction. All right. So T1 then, how is that direction going to move? All right. Well, in T1, we're going to go like this. So note, the part of C will still be in its same direction. L2 will go in this direction. K1, note we're going to go in the reverse direction of what K originally was. And L1, we're going to go in that direction. Okay. So C is the curve we're starting with, where we're trying to figure out how to integrate on, so that's the direction we picked for it. And K is inside of it, and we're just going to choose the same direction. But when we split it into the parts T1 and T2, note where direction on K has changed. All right, C2, well, if I want to go this direction to keep the orientation the same from C, all right, well, then note that I'll reverse myself on L. I'm going to be going the opposite direction that K is originally going. And L2 is also reversed of the direction there. So, and that's L1 right there. Okay, so now when I integrate on T2, so I'm going to pick up the integral of C2, I'm going to pick up the integral of K2 here. But note, L1 and L2, I'm going to pick up those integrals, but in the reverse direction. So what I'll actually pick up here, okay, so I'm going to pick up C2, but the L's, I'm actually going to get the negative of them. because the direction was reversed. Okay. So again, I'm picking up the negatives of the integrals of L because the integrals that I had in the first one were going in one direction, the integrals in the next one are going the opposite one, so they're negative. All right, so note this expression right here, note this expression right there. When I add them together, the L's are going to drop out. C1 plus C2, K1 plus K2. Okay. All right, so add them. And we'll have 0, and then we'll have the integral of C1 of f of z plus the integral of C2, and the integral of K1, and the integral of K2. Okay. So now, what does this get us? So if we go back to the two pictures that we have, C1 and C2 glued together just give us C. K1 and K2 glued together give us K, but they give us K in the reverse direction. So these two added together give me the integral on C. Oh, and these should not be closed integrals. Sorry about that. Too excited to draw those out. These are, of course, integrals and just curves. C1, C2, K1, K2. And so the C1 and the C2 give me the integral on the closed curve C, and adding K1 and K2 give me the integral on K, but in its reverse direction, so we get the negative of it. And so the big punchline here is that the integral on C is the same as the integral on K. Okay. So, the thing you are obviously asking right now is, oh my god, who the hell cares? And the answer to that is we do. Right? Because what have we established now using Cauchy-Grosset? What we've established is that if I wanted to compute the integral of a function on a simple closed curve, and I don't know that it's analytic everywhere, but I can put another curve inside where outside of that curve I can guarantee analyticity, well now integrating on C is the same thing as integrating on K. And if I cleverly choose my K, I'm going to have a much easier time computing the integral of C. And also note in general, this does reveal that if I'm trying to integrate on a closed curve C, I can always turn it into another curve K. Right, and this is actually called, this usually gets a name, our book I don't think gives it a name, but usually gets referred to as the principle of deformation of curves or something to that effect. So let us use this now to solve a problem. Okay, so let's go back to this here, and let's do this where C is the following curve. Three I minus 3 minus 3I. Z, 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 z. All right, so let's say I wanted to integrate 1 over z minus I, and the simple closed curve that we're working on is the square that goes through those points right there. Yeah. All right, now, there's a bit of a problem, right? Because, hey, simple closed curve, if my function is nice and analytic, the integral should equal 0. However, note, we got a bit of a problem. The exact point where this function fails to be analytic is enclosed inside of the curve. Now note, I can integrate this function on that curve because the curve does not go through the point I, so there's no point where this is undefined. This is a well-defined integral. Right, the problem is I just can't use Cauchy-Grosset to solve this. But I now know that, well, if I wanted to integrate this function, which fails to be analytic on C, I just need to now find a curve where outside of the curve, my function remains analytic. So for our homework, we looked at an integral like this, and the curve C was something really nice. It was a circle. So how about we replace our curve C here with our curve K here, which will be a nice little circle centered at the exact spot we have a problem, and we'll just pick some radius to get us inside of there. The radius will literally not matter. So we know that this needs to equal now the integral on this nice little curve K, and I claim that this integral is actually something we can compute. So let's actually do that.